What if I told you that right now, galaxies are racing away from us faster than the speed of light? Not just a few countless galaxies, stretching into the infinite dark, vanishing beyond the cosmic horizon, as if the universe itself is playing a game of keep away. This isn't science fiction, it's the reality of our expanding cosmos, a phenomenon so bizarre it defies our deepest intuitions about space, time, and the very fabric of existence. And here's the kicker, we still don't fully understand why. The universe isn't just growing, it's accelerating, as if some invisible hand is pressing harder on the gas pedal with every passing second. Scientists call this mysterious force dark energy, a placeholder name for something that makes up nearly 70% of the cosmos yet remains utterly invisible, undetectable, and unexplained. But dark energy is just the beginning. From the mind-bending nature of the Hubble tension to the eerie fine-tuning of the universe's expansion rate, there are at least 25 colossal questions that keep astronomers awake at night, puzzles so profound they challenge everything we think we know about reality. So today, we're diving into the greatest unsolved mysteries of cosmic expansion. Why is the universe speeding up? What's really happening in the voids between galaxies? Could there be other dimensions tugging at the fabric of space-time? These aren't just academic curiosities, they're clues to the ultimate fate of everything: stars, planets, even time itself. And the wildest part, some of these answers might be hiding in plain sight, waiting for someone, maybe even you, to connect the dots. So buckle up. We're about to explore the edges of known science, where every question leads to deeper wonder, and every answer only reveals how much we have left to discover. One of the most baffling puzzles in modern cosmology is this: the universe isn't just expanding, it's doing so at a rate that flatly contradicts our best predictions. Scientists call this the Hubble tension, a cosmic tug of war between two sets of measurements that refuse to agree. On one side, we have observations of the cosmic microwave background, the faint glow left over from the Big Bang. These measurements suggest a specific expansion rate, one that fits neatly with our understanding of dark energy and the universe's early moments. But on the other side, when astronomers track distant supernova or pulsating stars called Cepheid variables, they get a different number altogether, a faster, more aggressive expansion rate that throws all our models into question. Think of it like trying to measure the speed of a car with two different speedometers, only to realize they're giving wildly different readings, and no one can figure out why. The discrepancy might seem small, but in cosmology, even a tiny mismatch can signal a fundamental flaw in our understanding. Could dark energy be evolving over time, growing stronger as the universe ages? Or is there something deeply wrong with our theories of gravity, forcing us to rewrite Einstein's equations? Some researchers even speculate that we're seeing hints of unknown particles or extra dimensions subtly warping the fabric of space. The implications are staggering. If the faster rate is correct, it means the universe is hurtling toward an even more extreme fate, a big rip where galaxies, stars, and eventually atoms themselves are torn apart by runaway expansion. But if the slower rate holds, we might need to rethink dark energy entirely, opening the door to concepts we haven't even imagined yet. Right now, no one has the answer. Telescopes like the James Webb Space Telescope are peering deeper into the cosmos, hunting for clues, but the mystery remains. And that's what makes this so thrilling, because every disagreement in science is an opportunity for a revolution. If dark energy is the invisible hand pushing the universe apart, then why does it feel like we're trying to grasp smoke? This mysterious force was discovered in the late 1990s when astronomers made a shocking observation: distant supernovae were dimmer than expected, meaning they were farther away than our models predicted. The universe wasn't just expanding, it was doing so faster and faster, as if some anti-gravity were at work. the leading explanation, dark energy, a term that hides our ignorance more than it reveals knowledge. Einstein might have been the first to stumble upon the idea, though he famously called it his greatest blunder. He introduced the cosmological constant, a sort of mathematical fudge factor, to keep the universe static in his equations. When Edwin Hubble proved the universe was actually expanding, Einstein abandoned the concept, but now it's back in play as a possible candidate for dark energy, a constant, unchanging energy woven into space itself. The problem: the predicted value of this energy is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. In other words, our best theories and observations don't just disagree, they're catastrophically, unimaginably wrong. Then there's quintessence, a more exotic idea. Unlike the static cosmological constant, quintessence is a dynamic field that changes over time, growing stronger or weaker as the universe evolves. Imagine squeezing a balloon. Sometimes the pressure inside resists more, sometimes less. If dark energy behaves this way, it could explain why the expansion rate seems to vary. But here's the catch: no one has detected any evidence of such a field, and its properties remain purely hypothetical. Another contender is vacuum energy, the idea that empty space isn't empty at all. Quantum mechanics tells us that even a perfect vacuum crackles with virtual particles popping in and out of existence. This seething energy could be fueling cosmic acceleration, except once again, the math doesn't add up. Calculations suggest vacuum energy should be unimaginably stronger than what we observe. It's like expecting a hurricane and feeling only a breeze. The truth is, we're still grasping in the dark. Every explanation we have comes with glaring holes, forcing us to question whether we're missing something fundamental. Could dark energy be a sign of extra dimensions warping space-time, a glitch in our understanding of gravity, or is it something entirely beyond our current physics? Right now, all we know is that it's out there, silent, invisible, and utterly relentless, stretching the universe toward an unknown destiny. But what if dark energy isn't the constant force we've assumed it to be? The unsettling possibility that it might be growing stronger or weaker over time could unravel our entire cosmic playbook. This isn't just speculation, it's a question astronomers are racing to answer by scrutinizing two cosmic yardsticks: the explosive deaths of stars called Type Ia supernova and the ghostly fingerprints of ancient sound waves frozen in space known as baryon acoustic oscillations. Type Ia supernova are the universe's standard candle stellar explosions, so consistent in brightness that they let us measure distances across billions of light years. In the late 1990s, these very explosions revealed cosmic acceleration. Now they might hold clues to whether dark energy is shifting. Imagine a light bulb that dims unpredictably. If supernovae at different eras of the universe appear brighter or fainter than expected, it could mean dark energy's push has changed over cosmic history. Some data hints at exactly that: an odd drift in supernova brightness patterns that doesn't fit a static dark energy model. Could this be the first whisper of a dynamic force, one that ebbs and flows like tides in the fabric of space itself? Then there are baryon acoustic oscillations, the cosmic echoes of pressure waves from the universe's infancy. These leave a faint grid-like pattern in the distribution of galaxies, acting as a ruler for measuring expansion across time. Recent surveys suggest this ruler might be stretching differently than dark energy's constant theory predicts. If confirmed, it would mean the universe's acceleration isn't steady. It's a roller coaster, with dark energy's grip tightening or loosening over epochs. A changing dark energy would rewrite cosmology's rules. The cosmological constant, Einstein's static placeholder, would crumble, replaced by theories like quintessence, where dark energy is a fluid-like field with mutable properties. Some models even propose that dark energy could eventually flip its effect, collapsing the universe in a big crunch. But here's the catch: every anomaly could also be a mirage. Dust distorts supernova measurements and galaxy surveys battle statistical noise. The next generation of telescopes, like the Vera Rubin Observatory, aims to cut through the fog with petabytes of fresh data. Until then, we're left with a tantalizing maybe, a universe where the rules might not just be unknown but ever shifting. Could the real answer to cosmic expansion lie not in some mysterious dark energy, but in our incomplete understanding of gravity itself? That's the radical proposition of modified gravity theories, ideas that rewrite Einstein's rules to explain the universe's acceleration without invoking dark energy at all. Take MOND, short for modified Newtonian dynamics. This framework suggests that gravity behaves differently on colossal scales than it does in our solar system. Instead of relying on invisible energy to explain galaxy rotations or cosmic expansion, MOND tweaks the math so gravity weakens less abruptly over vast distances. It's like discovering the rules of chess change subtly when the board expands a small adjustment with universe-altering consequences. Then there's F of R gravity, an even more exotic twist. Here, gravity's strength isn't fixed. It depends on the curvature of space-time itself. Picture a rubber sheet that stiffens or relaxes depending on how much it's stretched. In regions of low density like the cavernous voids between galaxies, this altered gravity could mimic the effects of dark energy, pushing space apart without any need for phantom forces. Early simulations show promise, but there's a catch. These theories struggle to explain every observation simultaneously, like the precise patterns in the cosmic microwave background. Still, the allure is undeniable. If correct, they'd overthrow a century of assumptions, proving that Einstein's masterpiece, while brilliant, might be an incomplete chapter in a grander story. But what if dark energy isn't just real, but far stranger than we've imagined? Enter phantom energy, a hypothetical variant so potent it makes today's cosmic acceleration look gentle. Unlike ordinary dark energy, which stays constant, phantom energy could grow denser as the universe expands. This creates a terrifying feedback loop. The more space stretches, the stronger phantom energy becomes, accelerating expansion further until, in a finale dubbed the Big Rip, even atomic bonds snap. Stars, planets, and eventually the fabric of matter itself would be shredded in a finite time. Some calculations suggest this could happen in as little as 20 billion years, a blink on cosmic scales. Theorists debate whether phantom energy is plausible or just a mathematical nightmare. Its existence would require exotic physics like negative kinetic energy, a substance that gains strength as it's stretched, defying everyday intuition. Yet it can't be ruled out. Observations of supernova and galaxy clusters occasionally show anomalies that phantom energy might explain, though the evidence remains tentative. Whether it's a real threat or a cosmic ghost story, one thing is clear: the universe holds mysteries that could reshape our destiny in ways we're only beginning to fathom. Between modified gravity's elegant revisions and phantom energy's apocalyptic edge, these alternatives remind us how much is still unknown. Every explanation comes with tantalizing clues and glaring gaps, leaving scientists chasing shadows at the frontier of physics. The next decade of telescopes and sky surveys might tip the scales, or reveal something entirely unexpected, proving once again that the cosmos thrives on keeping us guessing. Look up at the night sky and you'll notice something strange. No matter which direction you face, the universe appears eerily uniform. Galaxies cluster in similar patterns, and even the ancient light from opposite edges of the cosmos shows nearly identical temperatures. This cosmic symmetry shouldn't exist. Here's why. If you calculate the time since the Big Bang, there hasn't been enough seconds for heat or information to travel between these distant regions. It's like walking into two bakeries on opposite sides of the planet and finding identical loaves of bread down to the last crumb, even though the bakers never spoke or shared recipes. Scientists call this the horizon problem, and it's one of the deepest riddles in cosmology. The leading solution for decades has been inflation theory, the idea that the infant universe underwent a fleeting, exponential growth spurt, stretching a subatomic speck to cosmic proportions in less than a trillionth of a second. This rapid expansion could have smoothed out temperature differences before space-time had time to create horizons, like stretching a wrinkled balloon until its surface appears flawless. But inflation isn't perfect. For one, it's nearly impossible to test directly. The energy scales involved are so extreme they dwarf anything our particle colliders can recreate. Worse, inflation predicts a multiverse, an infinite froth of bubble universes with random physical constants, a concept so untestable it borders on philosophy. Some physicists argue this makes inflation less a scientific theory and more a metaphysical placeholder. That's why alternatives are gaining traction. Take bouncing cosmologies, which propose that the Big Bang wasn't a true beginning but a rebound from a previous collapse. In this scenario, the universe's uniformity comes from a slow, pre-bang smoothing process during the contraction phase, like kneading dough until it's perfectly even. Others suggest we're seeing quantum entanglement on a cosmic scale, that distant regions of space were once intimately connected before inflation blew them apart, preserving their symmetry like split twins sharing a hidden bond. Then there's the holographic principle, a radical idea that our three-dimensional universe might be a projection of information encoded on a distant two-dimensional surface. If true, uniformity could emerge from deeper, hidden laws we're only beginning to glimpse. Each of these theories dances at the edge of known physics, challenging not just how we see the cosmos, but what we think reality even is. The horizon problem isn't just about temperature. It's a window into whether our universe's structure is a fluke, a necessity, or something stranger than we've dared to imagine. Imagine the universe as a balloon, one that inflated so rapidly. It went from smaller than an atom to the size of a grapefruit in less time than it takes light to cross a single proton. This is cosmic inflation, the theoretical heartbeat of the early cosmos. A burst of expansion so violent it makes today's accelerating universe seem sluggish by comparison. The numbers are staggering. Space itself grew by a factor of 10 to the power of 78 in volume, all within a fraction of a second after the Big Bang. But here's the puzzle: what could possibly unleash such an eruption of space-time? The leading suspect is something called the inflaton field, an invisible energy saturating the infant universe like syrup soaking a sponge. Picture this field as a cosmic hilltop. As long as the inflaton perched high on that slope, its immense potential energy drove space apart at an exponential rate. But just as a ball eventually rolls downhill, the inflaton lost energy, decaying into the particles and radiation that would later form stars and galaxies. This transition wasn't smooth. Quantum fluctuations jostled the field, creating microscopic ripples in space-time. Those ripples, stretched to cosmic scales by inflation, became the seeds for all the structure we see today: the galaxies, the voids, even the faint temperature variations in the cosmic microwave background. Yet for all its explanatory power, inflation remains maddeningly elusive. Unlike the Big Bang's afterglow, which we can still detect, inflation's fingerprints are indirect. The quantum fluctuations it spawned are preserved in the cosmic microwave background, like fossilized raindrops in ancient rock. But the inflaton field itself has vanished, leaving no trace beyond its aftermath. Some theorists argue this makes inflation untestable, more a narrative convenience than hard science. Others hunt for subtle clues, like primordial gravitational waves, undulations in space-time that could carry echoes of inflation's final moments. Experiments like the BICEP array at the South Pole scan the sky for these whispers, but so far the signals remain buried in noise. The stakes couldn't be higher. If inflation happened, it reshaped not just space but reality's very rules. Some models suggest it never truly ended, that our universe is just one bubble in an endless froth of inflating space, each with different physical laws. Others propose wilder ideas, like a cyclical universe where inflation resets the cosmic clock with each new cycle. Without direct proof, these remain speculative, leaving us with a haunting question. Did inflation forge the universe as we know it, or are we chasing the shadow of something far stranger? The answer lies hidden in the first unimaginable fraction of a second, a moment so brief yet so consequential it might hold the key to everything. What if our universe is just one bubble in an endless cosmic froth, with entirely different laws of physics reigning in each pocket? This is the staggering possibility of eternal inflation, a twist on the standard inflation theory that suggests the rapid expansion of space didn't just happen once, but keeps happening eternally, birthing countless universes in its wake. Picture a pot of boiling water where every rising bubble is a self-contained cosmos, each with its own unique properties. Some might have stronger gravity, others might lack dark energy entirely, and a few could even harbor physics so alien that matter as we know it couldn't exist. The idea hinges on inflation's quirks. According to quantum theory, the inflatoned field, the energy driving inflation, wouldn't decay uniformly. Some regions would roll downhill faster, settling into stable states that stop inflating and form bubble universes like ours. But other patches caught in higher energy states would keep expanding exponentially, spawning new bubbles ad infinitum. The result, a fractal multiverse where creation never stops and most of reality remains forever out of reach, separated by stretches of hyper-inflating space that light can never cross. The catch: observational evidence is non-existent. By definition, these other universes are causally disconnected from ours. No signal, no light, no gravity could traverse the inflating gaps between them. Some scientists argue this makes the multiverse untestable, more metaphysics than physics. Others counter that subtle signatures might linger in our own universe, like collisions between neighboring bubbles that left scars in the cosmic microwave background. Satellite data has hunted for these imprints, but so far nothing conclusive has turned up. Philosophers weigh in too. If a theory predicts infinite unseen universes, can it ever truly be falsified? Or does it become a theory of anything, adaptable to any observation? The debate cuts to the heart of what science is, a system for making predictions about the world we can see. Yet the allure persists because if eternal inflation is real, it could explain cosmic fine-tuning. Why does our universe have such perfectly balanced constants for life? Simple, we're just one lucky bubble in an unfathomable sea of possibilities. For now, eternal inflation remains a tantalizing what if. It stretches our imagination to the breaking point, challenging not just how we see the cosmos, but what we think science can even address. Whether a profound truth or a beautiful dead end, it forces us to confront the greatest mystery of all. Are we alone in existence, or just one note in an infinite cosmic symphony? The universe is dying not with a bang, but with a whimper. Or is it? The ultimate fate of everything depends on a cosmic tug of war between dark energy's relentless push and gravity's pull, and right now we're not sure which force will win. Let's break down the three most chilling possibilities, each more dramatic than the last. First, the big freeze, also called the heat death. Here, dark energy keeps accelerating expansion until galaxies are torn beyond the cosmic horizon, leaving every star system marooned in infinite darkness. As space stretches, even the energy of particles will dilute to near nothingness. Picture a cup of coffee left out forever. It doesn't vanish, but grows so cold and thin it might as well be empty. This scenario assumes dark energy stays constant, as the cosmological constant suggests. Stars will burn out, black holes will evaporate via Hawking radiation, and after uncountable trillions of years, the universe will settle into a lifeless equilibrium where not even quantum fluctuations stir the void. But what if dark energy isn't constant? Enter the Big Crunch, a cosmic reversal where gravity finally overpowers expansion. If dark energy weakens over time, or if the universe has enough mass to curve back on itself, everything will collapse inward. Galaxies would merge in a fiery ballet, temperatures skyrocketing until atoms themselves unravel. Space-time would crumple like paper thrown into a fire, potentially recycling into a new Big Bang. Some theories even suggest this could be part of an endless cycle, with universes breathing in and out like lungs. The critical factor, the universe's curvature. Right now, measurements suggest space is flat, but if future telescopes detect even slight positive curvature, the crunch becomes a real possibility. Then there's the most violent finale, the Big Rip. If dark energy is phantom energy growing stronger as space expands, it could eventually overwhelm all fundamental forces. First, galaxy clusters would be ripped apart, then individual galaxies. Around 3 months before doomsday, solar systems would unravel. Planets would detach from their stars. In the last minutes, stars and planets themselves would disintegrate. Atoms would be shredded nanoseconds before the end, as the exponential acceleration tears space-time itself apart. Time would lose all meaning in a singularity of infinite expansion. Which scenario is most likely? Current data leans toward the Big Freeze, given dark energy's apparent consistency and the universe's flat geometry. But here's the twist: we're measuring these parameters with less than 1% precision. The slightest error could flip the script entirely. Future missions like the European Space Agency's Euclid telescope aim to map dark energy's behavior across 10 billion light-years, searching for clues in the warped light of distant galaxies. Until then, the universe's fate hangs in the balance, a reminder that even in the vastness of space, the tiniest uncertainty can change everything. Is the universe infinite, stretching forever into the endless dark? Or is it finite, a vast but bounded cosmic island floating in something even stranger? This isn't just philosophy, it's a question scientists are racing to answer by mapping the very shape of reality itself. The key lies in cosmic topology, the study of the universe's geometry, and the latest data from missions like the Planck satellite have thrown the debate wide open. For decades, astronomers assumed the universe was flat, not like a sheet of paper, but in the sense that parallel lines stay parallel forever, and the angles of a triangle always add up to 180 degrees. A flat universe implies infinite space with no edge or boundary, but Planck's precise measurements of the cosmic microwave background revealed a tantalizing anomaly, a slight but persistent preference for closed geometry, where space curves gently back on itself like the surface of a four-dimensional sphere. In such a universe, if you traveled far enough in one direction, you'd eventually return to your starting point, not because space loops like a video game, but because gravity bends the fabric of reality into a finite yet unbounded whole. The implications are staggering. A closed universe could mean everything we see is just a fraction of a grander structure, like ants crawling on a globe unaware of its true shape. But here's the catch: the curvature Planck detected is incredibly subtle, just a 1% deviation from perfect flatness. Critics argue this could be statistical noise or systematic errors in the data. Other observations, like the clustering of galaxies and the bending of light around massive objects, overwhelmingly favor flatness. The tension between these datasets has sparked fierce debates, some researchers even proposing that the discrepancy hints at unknown physics, like exotic dark matter or a flaw in our understanding of inflation. Then there's the topology question. Even if the universe is finite, its shape might be far more complex than a simple sphere. Imagine a cosmic kaleidoscope. Space could fold into intricate configurations, like a three-dimensional torus, a donut shape, or a hyperbolic maze where identical patterns repeat across vast distances. Some theories suggest we might spot these repetitions in the cosmic microwave background: ghostly circles in the sky, where the same temperature fluctuations appear in multiple locations, evidence that light has wrapped around the universe. So far, searchers have come up empty, but the hunt continues. At the heart of this puzzle is a deeper mystery. What does finite even mean in a universe that's expanding? If space is stretching, does its volume grow, or just the distances within it? Could infinity be an illusion, a trick of scale? For now, the data keeps us guessing, dangling between two equally mind-bending possibilities. Either answer redefines our place in the cosmos, whether we're adrift in an unbounded sea of existence or part of a colossal, yet closed, cosmic symphony. The universe's shape isn't just about geometry. It's a reflection of reality's deepest nature, and we're only beginning to trace its edges. When the universe was born, matter and antimatter should have annihilated each other in a flash of pure energy, leaving behind nothing but a featureless void. Yet here we are, made of matter, surrounded by matter, in a cosmos dominated by matter. This baffling asymmetry is one of physics' greatest unsolved mysteries, and it holds the key to understanding how the expanding universe took shape. The imbalance is called Baryon asymmetry, and the numbers defy belief. For every billion matter-antimatter pairs created in the Big Bang, one extra particle of matter slipped through. That tiny fraction, just a 1 in a billion excess, was enough to seed every star, planet, and galaxy we see today. Without it, the universe would be an empty sea of radiation. So how did matter cheat annihilation? The answer might lie in a phenomenon called CP violation, where nature treats particles and their mirror image antiparticles slightly differently. In the 1960s, experiments with subatomic kaons revealed the first cracks in the symmetry between matter and antimatter. Certain particle decays favored matter over antimatter by a razor-thin margin far too small to explain the universe's staggering imbalance. Theorists proposed a solution: leptogenesis, a process where ultra-heavy neutrinos decayed asymmetrically in the early universe, producing more electrons than positrons. These electrons then tipped the scales, biasing quark interactions to favor matter. It's like a cosmic casino where the house always wins, except here, the house is the universe's hidden laws quietly skewing the odds. The stakes couldn't be higher. If matter and antimatter had been perfectly balanced, the universe would have self-destructed before expansion could even begin. Instead, that slight asymmetry fueled the fires of cosmic evolution. As space stretched, the leftover matter clumped under gravity, forming the first hydrogen clouds that would ignite into stars. Even the distribution of galaxies today, woven into vast filaments and voids, traces back to those initial quantum fluctuations amplified by inflation and shaped by the matter-antimatter divide. But here's the twist: despite decades of searching, we've only found enough CP violation to account for a fraction of the observed asymmetry. Experiments like the Large Hadron Collider are hunting for exotic particles that might hold the missing clues, while observatories scour the cosmos for antimatter pockets that could rewrite the story. Every answer only deepens the mystery, reminding us that the universe didn't just expand, it cheated, and we're still trying to figure out how. The cosmic microwave background, the afterglow of the Big Bang, should be uniform, a near-perfect snapshot of the universe's fiery infancy. Yet when scientists stare into this ancient light, they find eerie imperfections, glitches in the cosmic code that refuse to fit the standard story. Take the infamous cold spot, a sprawling region of the sky where temperatures dip unexpectedly, as if someone turned down the thermostat in a corner of the newborn universe. Stretching over 1 billion light-years, this anomaly defies simple explanations. Is it a statistical fluke, a rare but natural fluctuation in the primordial plasma? Or could it be something far stranger, a bruise left by a collision with another universe? Then there's the dipole asymmetry, a baffling lopsidedness in the CMB's temperature map. One hemisphere of the sky appears slightly warmer than the other, as if the entire universe were moving in a particular direction at breakneck speed. But here's the catch: This motion can't be explained by the known distribution of galaxies or dark matter. Some theorists suggest it's evidence of a vast, unseen structure beyond the observable universe, a gravitational titan tugging at the fabric of space-time. Others propose a radical alternative, that our universe is caught in the wake of a neighboring bubble universe, its invisible influence warping our local cosmos like a ship's bow wave. Skeptics argue these anomalies could stem from mundane sources. Instrumental noise, foreground dust, or even subtle errors in data processing might mimic cosmic mysteries. The Planck satellite's painstaking observations have ruled out some artifacts, but uncertainties linger. What makes these puzzles so electrifying is their potential to upend cosmology. If the cold spot truly marks a multiverse collision, it would be the first empirical hint of realities beyond our own. The dipole asymmetry, if confirmed as primordial, might force us to rewrite inflation's playbook, suggesting the early universe wasn't as uniform as we thought. Yet the most tantalizing possibility is that we're seeing the limits of our theories. The standard model of cosmology, inflation, dark matter, dark energy, has been stunningly successful, but these anomalies whisper that it might be incomplete. Future observatories, like the Simons Observatory in Chile, will scan the CMB with unprecedented precision, hunting for patterns that could distinguish between cosmic ghosts and genuine breakthroughs. Until then, these quirks in the oldest light remind us that even the universe's baby photos hold secrets we've only begun to decipher. What if the very laws of physics aren't constant at all, but shifting imperceptibly across cosmic time? This unsettling possibility challenges one of science's bedrock assumptions, that numbers like the fine structure constant, which governs how light and matter interact, are immutable, woven into the fabric of reality since the Big Bang. Yet when astronomers train their telescopes on quasars, the blazing hearts of distant galaxies, they're finding hints that these constants might be anything but. Quasars act as cosmic backlights. As their light traverses billions of light years, it passes through ancient gas clouds that absorb specific wavelengths, leaving fingerprints in the spectrum. By comparing these absorption lines to lab measurements, scientists can check if the fine structure constant denoted by the Greek letter alpha held the same value when the universe was half its current age. The results are contentious. Some teams report slight deviations in alpha at the level of just a few parts per million, as if the strength of electromagnetism were subtly weaker in the past. Others see no change at all, attributing the anomalies to calibration errors or interstellar gas dynamics. If the variations are real, the implications would ripple across cosmology. A changing alpha could mean that dark energy's push isn't constant. It might evolve alongside these fundamental parameters, rewriting our models of cosmic acceleration. Some theories even suggest extra dimensions could be leaking influence into our universe, gently tweaking physics over eons. Picture a piano whose keys retune themselves over centuries, playing the same cosmic symphony, but in ever so slightly different harmonies. The debate hinges on precision. Modern spectrographs like the Very Large Telescope's espresso instrument can measure wavelength shifts equivalent to a snail's pace compared to light speed. Yet the universe loves to obscure its secrets. Magnetic fields in those ancient gas clouds might mimic alpha's effects, while subtle quirks in quasar light could masquerade as shifts. To settle the controversy, astronomers are turning to new probes, molecular clouds that act as ultra-sensitive rulers, and atomic clocks so precise they could detect alpha's drift over mere decades. What makes this quest so electrifying isn't just the potential discovery, it's the philosophical quake it would trigger. Constants are the foundation upon which we've built our understanding of reality. If they're mutable, the cosmos becomes a far stranger place, a realm where the rules themselves evolve, and where the universe's expansion might be written in ink that slowly fades. Until we know for certain, every measurement is a whisper from the depths of time, hinting that we might be standing on shifting sands. We know dark matter exists because we can see its grip on galaxies, literally. Stars orbit the centers of spiral galaxies so fast that, by all rights, they should fling themselves into the void, the only thing holding them in place. An invisible cosmic scaffolding, dark matter whose gravity outweighs ordinary matter 5-to-1. But here's the kicker, we still don't know what it's made of. This isn't just a gap in our knowledge, it's a chasm, one that could redefine how we understand the universe's expansion. Take WIMP, or weakly interacting massive particles, the long-standing frontrunners in the dark matter hunt. These hypothetical particles would be heavy, slow-moving relics from the Big Bang, barely interacting with normal matter except through gravity. Underground detectors like LUX Zeppelin are hunting for the rare flicker of a WIMP colliding with an atom, while the Large Hadron Collider smashes protons together, hoping to conjure them into existence. But decades of searching have turned up empty. The lack of a signal has some physicists whispering that WIMP might be a dead end, a beautiful theory trapped in an unforgiving universe. Then there are actions, the dark matter dark horse. These ultra-light particles were originally dreamed up to solve a totally different problem in quantum physics, but their ghostly properties fit the bill. They'd barely interact with light or matter, yet could collectively weave the gravitational web holding galaxies together. Experiments like ADMS are tuning microwave cavities, hoping to catch actions converting into photons in the presence of strong magnetic fields. It's like listening for a cosmic whisper in a hurricane of noise, but if they succeed, it would crack two mysteries at once. But dark matter's identity isn't just academic trivia, it shapes the universe's fate. Cold, slow-moving particles like WIMP would have clumped early in cosmic history, sculpting the vast filaments and voids we see today. Hotter, faster dark matter would have smoothed out those structures, leaving a fundamentally different cosmos. The missing satellites problem highlights this puzzle. Our simulations predict thousands of dwarf galaxies orbiting the Milky Way, yet we've only found a few dozen. Is dark matter warmer than we thought, suppressing small-scale clumps? Or are we overlooking swarms of invisible, starless halos? The answer might lie in the quirks of galaxy rotation curves. Some dwarf galaxies rotate so slowly that they shouldn't hold onto their gas clouds unless dark matter is fluffy, with a diffuse core that cradles them gently. Others, like the ultra-diffuse galaxy Dragonfly 44, are 99% dark matter by mass, yet somehow avoid collapsing into dense knots. These outliers defy the standard playbook, hinting that dark matter might have complex interactions we've yet to imagine, perhaps even a hidden force that only affects itself. Every dead end in the lab, every anomaly in the sky forces us to reconsider. Could dark matter be primordial black holes forged in the chaos of the Big Bang? Or something entirely beyond particles, a shadow universe with its own physics, barely tethered to ours? The longer the mystery persists, the clearer it becomes. Dark matter isn't just a placeholder in our equations. It's the architect of cosmic structure, the silent partner in expansion, and the key to understanding why the universe looks the way it does. Until we crack its code, we're staring at a half-finished blueprint, wondering what the rest of the design holds. What if some of the universe's darkest secrets are hiding in plain sight, not as exotic particles or elusive energy fields, but as ancient black holes forged in the first chaotic moments after the Big Bang? These hypothetical objects, known as primordial black holes, could be lurking throughout the cosmos, invisible yet massive enough to reshape galaxies, twist the paths of light, and even throw off our measurements of cosmic expansion. Unlike the black holes we're familiar with, those born from collapsing stars, primordial black holes would have emerged from the unimaginable density fluctuations in the infant universe. Picture the cosmos 1 second old, a seething plasma so hot and dense that random pockets could have collapsed under their own gravity, forming black holes with masses ranging from a speck of dust to 100,000 suns. Some theories suggest these relics could account for part, or even all of, the dark matter we've been chasing for decades. Their impact on cosmic expansion would be subtle but profound. If enough primordial black holes existed, their collective gravity would tug at the fabric of space, subtly altering how galaxies move apart over time. Measurements of supernova or baryon acoustic oscillations might carry hidden signatures of this influence, like ripples in a pond betraying unseen stones beneath the surface. Even more intriguing, some primordial black holes could have evaporated by now, thanks to Hawking radiation, leaving behind faint bursts of gamma rays or distorting the cosmic microwave background in ways we're only beginning to track. Then there's their role in galaxy formation. These ancient black holes could have acted as cosmic seeds, their gravity accelerating the collapse of gas clouds into the first stars and galaxies. Computer simulations show that if even a tiny fraction of primordial black holes survived, they'd sink to the centers of galaxies, merging over eons to form the supermassive black holes we observe today, like quasars shining from the universe's edge. But here's the puzzle. If they're everywhere, why haven't we seen them? The hunt is on. Telescopes scour the skies for micro-lensing events, brief flashes caused by a primordial black hole passing in front of a star and bending its light. Gravitational wave detectors listen for the quiet chirps of mergers between these relics, while researchers analyze the cosmic microwave background for odd imprints. So far, the evidence is elusive, but the possibilities are too tantalizing to ignore. Whether they're missing pieces of the dark matter puzzle or ghosts from the universe's first breath, primordial black holes remind us that sometimes the boldest answers hide in the oldest shadows. Galaxies don't just scatter randomly across the cosmos, they gather in sprawling, luminous threads, weaving a web so vast it defies human scale. These filaments stretch hundreds of millions of light years, punctuated by glittering clusters where galaxies swarm like bees around honey. Between them lie the voids, deserts of near-nothingness so empty that if you stood in one, the night sky would appear almost starless. But why does the universe arrange itself this way? The answer is written in the ripples of the Big Bang and twisted by the relentless tug of cosmic expansion. Rewind to the universe's first moments. Quantum fluctuations, tiny, random variations in density, were stretched to cosmic proportions by inflation, imprinting faint fingerprints in the newborn cosmos. These ripples became the seeds of structure, with slightly denser regions pulling in more matter through gravity over billions of years. Dark matter, invisible and pervasive, acted as scaffolding, guiding ordinary gas and dust into its embrace until stars ignited and galaxies flickered to life. But here's where expansion throws a wrench into the story. As dark energy accelerates the universe's growth, it's not just pushing galaxies apart, it's reshaping the very architecture of the cosmic web. The Hubble tension, the mismatch in expansion rate measurements, hints that something's off in our models. If the universe is expanding faster than we thought, gravity's tug might be weaker on the largest scales, leaving filaments thinner and voids emptier than simulations predict. Picture stretching a spiderweb pulled too fast and the delicate strands snap apart. Similarly, rapid expansion could be stifling the growth of galaxy clusters, leaving them smaller and more isolated than they should be. Observations back this up. Surveys like the Sloan Digital Sky Survey reveal voids that are too vast and galaxies that are oddly sparse at the edges of filaments, as if something's been erasing structure before it fully forms. Then there's the mystery of the KBC void, a gargantuan empty region 7 times wider than expected, where our Milky Way sits near the center. Is this just a statistical fluke, or could it be a sign that expansion's acceleration carved a hole this enormous? Some theorists speculate that dark energy isn't uniform, that it clumps like invisible clouds, leaving patches of space to expand faster than others. If true, it would mean the cosmic web isn't just a relic of the past. It's a living, shifting entity, still being sculpted by forces we barely understand. The stakes are cosmic. If galaxies form differently than our simulations predict, it could mean dark energy is more complex than a simple cosmological constant, or that gravity itself behaves strangely across vast distances. Upcoming telescopes like the Vera Rubin Observatory will map billions of galaxies, hunting for subtle distortions that might reveal the invisible hands at work. Until then, the cosmic web remains both a masterpiece and a riddle, its patterns whispering secrets about the universe's birth and its accelerating death. Before the first stars flickered to life, the universe plunged into a profound silence, a shadowy era astronomers call the cosmic dark ages. Picture a cosmos veiled in fog. Hydrogen gas, left over from the Big Bang, had cooled into a thick, neutral shroud, absorbing nearly all light. No stars, no galaxies, just an expanse so opaque that if you'd lived back then, your eyes would have seen nothing but endless black. This eerie twilight lasted for hundreds of millions of years until the first stellar fires burned away the gloom in a process called reionization. But here's the puzzle. The timeline of this transformation makes no sense unless we factor in the universe's accelerating expansion. Reionization began when the earliest stars, monstrously large and ferociously hot, unleashed floods of ultraviolet radiation. Like a cosmic sunrise, their light ripped electrons from hydrogen atoms, carving transparent bubbles in the fog. Over time, these bubbles merged, clearing the haze and allowing light to travel freely, a milestone we detect as subtle polarization patterns in the cosmic microwave background. The catch, based on the number of early galaxies we've spotted, there shouldn't have been enough stars to reionize the universe so quickly. Some models suggest the job required 10 times more ultraviolet light than our telescopes can account for. This is where dark energy throws a wrench into the story. If the universe expanded faster than we thought during this epoch, a possibility hinted at by the Hubble tension, it would have stretched the hydrogen gas thinner, making it easier for starlight to penetrate. Think of trying to burn through wet wood versus dry kindling. A more diffuse cosmos would have reionized faster, explaining the mismatch. But there's another twist. Rapid expansion might have also delayed the birth of the very stars needed to kickstart the process. As space stretched, gas would have taken longer to clump under gravity, postponing the moment when the first stars ignited. The Dark Ages weren't just a prelude, they were a battleground between gravity's pull and expansion's push. Telescopes like the James Webb Space Telescope are now peering back to this enigmatic era, hunting for faint galaxies that might resolve the paradox. Every dim speck of light they find rewrites our understanding of how the universe woke from its slumber and why the darkness lasted as long or as short as it did. The answers could redefine not just the past but the future of cosmic exploration. Time isn't just a backdrop to the universe, it's woven into the very fabric of space, bending and stretching under gravity's touch. But what happens when space itself is stretching? Could the universe's relentless expansion be subtly warping the flow of time, creating cosmic time zones where causality itself stutters? The answer might lie in Einstein's greatest revelation, general relativity. Picture two clocks, one anchored deep in a galaxy cluster where gravity's grip is strong, and another adrift in the void between galaxies where space is sparse and expanding faster. Relativity tells us the clock in the cluster would tick slower, weighed down by gravity's time-dragging effect. But here's the twist: expansion adds another layer. As space stretches, light from distant galaxies redshifts, its waves lengthening like taffy pulled thin. If time is tied to those waves like the rhythm of a cosmic metronome, could the universe's expansion also be diluting time's passage on vast scales? Some models suggest yes. In the voids where dark energy's push dominates, time might actually flow faster than in galaxy-rich regions. This isn't just theoretical musing. Astronomers have spotted quasars whose light variations appear eerily slowed when compared to nearby counterparts. Is this just an illusion caused by expansion? Or could we be seeing literal cosmic time dilation where the universe's acceleration stretches not just space, but the very ticks of its clock? The implications would rewrite causality. Events in one part of the cosmos could appear to unfold in slow motion from another, like a film reel played at half speed across billions of light years. Yet the greatest enigma isn't just how time bends, it's whether expansion could fray the thread of cause and effect. If two galaxies drift beyond each other's cosmic horizon, their light can no longer bridge the gap. Does that mean events in one become literally unconnected to the other, like islands drifting out of radio range? Some theorists argue that in such cases, causality itself splinters, creating patches of the universe forever cut off from each other's timelines. The wild card here is quantum mechanics. At tiny scales, particles can influence each other instantly, seemingly bypassing time's flow. Could expansion weave these quantum threads into the cosmic tapestry, allowing time's arrow to flex in ways we've yet to imagine? For now, these questions hover at the edge of testability, but as telescopes peer deeper into the void, they might catch time itself in the act, revealing a universe where not just space, but the rhythm of existence is in flux. Imagine gravity leaking into unseen realms, dimensions curled so tightly they're invisible to our eyes, yet tugging at the very fabric of space-time. This isn't the plot of a sci-fi novel. It's a serious hypothesis from string theory, the framework that suggests the universe might hum with extra dimensions beyond the four we know. If true, these hidden folds could hold the key to one of cosmology's greatest puzzles: why the universe's expansion defies our expectations. String theory proposes that all particles are minuscule vibrating strings, and for their math to work, they require at least 10 dimensions, 6 of which are compactified, coiled into geometric shapes smaller than an atom. While these dimensions are imperceptibly tiny in our everyday world, their influence might not be. At cosmic scales, gravity, the weakest of the fundamental forces, could be seeping into these extra dimensions, explaining why it seems to weaken over vast distances faster than our models predict. Picture water draining through a sieve. What if gravity's strength appears diluted because some of it is slipping into dimensions we can't see? This could account for the anomalous motions of galaxies and even dark energy's mysterious push, all without invoking unknown particles or energy fields. But how would extra dimensions alter expansion? In some models, these hidden realms aren't static. They could stretch or contract alongside our familiar three-dimensional space. As the universe grows, the compact dimensions might resonate like vibrating guitar strings, their oscillations subtly tweaking gravity's behavior across billions of light years. This could manifest as variations in the Hubble constant, or even explain why dark energy's effects seem so finely tuned, like a hidden hand adjusting the cosmos's expansion rate from behind the curtain. The most tantalizing clue might lie in gravity waves. When black holes collide, they send ripples through space-time that detectors like LIGO can measure. If extra dimensions exist, these waves might carry faint echoes of their structure, a barely perceptible shadow signal buried in the data. Similarly, particle colliders like the Large Hadron Collider could, in theory, produce micro-black holes that evaporate instantly, a smoking gun for dimensions beyond our own. So far, the evidence remains elusive, but the hunt is far from over. Critics argue that extra dimensions are a mathematical convenience, a way to patch over gaps in theories rather than a physical reality. Yet the possibility lingers, haunting the edges of cosmology. If proven, it would rewrite not just our understanding of expansion, but the nature of reality itself. Are we living in a higher dimensional universe that's only revealing fragments of its true shape? The answer might be hiding in the voids between galaxies, or in the quantum whispers of particles yet to be discovered, waiting to unravel the dimensions we've overlooked. The quantum realm is anything but calm. Even in the vacuum of empty space, particles flicker in and out of existence in a chaotic dance, borrowing energy from nothingness only to vanish in a heartbeat. These fleeting disruptions, known as quantum fluctuations, might seem insignificant, but they're the very reason you exist. During the universe's inflationary phase, when space expanded faster than light itself, these microscopic ripples were stretched to cosmic proportions, becoming the seeds for everything we see today: galaxies, stars, even the vast voids between them. Think of it like blowing up a balloon with tiny wrinkles on its surface. As the balloon inflates, those wrinkles grow into massive ridges and valleys. Similarly, the quantum jitters of the early universe were imprinted onto space-time, creating regions slightly denser or sparser than their surroundings. Over billions of years, gravity amplified these differences, pulling matter into the denser spots until they collapsed into galaxies, while the emptier regions stretched into the cosmic voids we observe now. The cosmic microwave background, the afterglow of the Big Bang, still bears the scars of these fluctuations, with temperature variations that precisely match the distribution of galaxies today. But here's where things get mind-bending. Quantum mechanics and gravity, the two pillars of modern physics, refuse to play nice when it comes to explaining how these fluctuations shape the universe. Quantum mechanics deals with the probabilistic, uncertain behavior of particles, while gravity, as described by Einstein's general relativity, is smooth and deterministic. During inflation, the universe was so unimaginably dense that quantum effects should have been entangled with gravity's grip, yet we have no theory that properly unites them. This is the quantum gravity problem, and it leaves a glaring hole in our understanding of cosmic expansion. Some theories attempt to bridge the gap. Loop quantum gravity suggests space-time is woven from discrete, indivisible threads, while string theory posits that particles are vibrating strings in a higher dimensional space. Yet none have produced testable predictions that explain why quantum fluctuations during inflation led to the specific patterns we see. Even more perplexing, why were these fluctuations so perfectly balanced? Too strong and matter would have clumped into black holes before stars could form. Too weak and galaxies might never have coalesced at all. The search for answers isn't just academic. If we can crack quantum gravity, we might finally understand whether inflation was a one-time event or part of an endless cycle, a universe rebounding from collapse or budding eternally into new realities. Telescopes like the Simons Observatory are scanning the cosmic microwave background for faint, swirling patterns called B-modes, which could carry echoes of primordial gravitational waves generated by quantum fluctuations. Detect those, and we'd have direct evidence linking the quantum realm to the cosmos's largest structures. Until then, we're left staring at a paradox. The universe's grand design seems written in quantum whispers, but the pen that wrote them remains missing. Every galaxy, every filament of the cosmic web, is a monument to those first chaotic instants, yet the rules governing them are still just beyond our grasp. Peering into the night sky, it's easy to assume the universe stretches infinitely in every direction, but what if it doesn't? What if there's an edge, a boundary beyond which space itself simply stops? The idea of a cosmic frontier isn't just science fiction. It's a serious puzzle astronomers grapple with, tangled in the very nature of light, time, and the limitations of observation. First, the paradox. Even if the universe is finite, we might never see its edge. Here's why. The speed of light, while blisteringly fast on human scales, is agonizingly slow across cosmic distances. The farthest light we can observe is the cosmic microwave background, a faint glow from when the universe was just 380,000 years old. Beyond that, the early cosmos was so dense and hot that light couldn't travel freely. It's like trying to see through a wall of fog. This means our observable universe is effectively a bubble, roughly 93 billion light-years across, with no guarantee of what lies beyond. If there is an edge, it's forever hidden behind an impenetrable curtain of primordial plasma. But what if the universe isn't infinite, just unimaginably large, like a colossal but finite balloon? In that case, the edge might not be a physical boundary at all, but a topological quirk. Imagine an ant crawling on the surface of that balloon. It could walk forever without hitting a wall, yet the space it explores is still finite. Similarly, our universe could curve back on itself in higher dimensions, making it boundless yet not infinite. If true, light from distant galaxies might even loop around this curved space, creating ghostly mirror images of the same stars in opposite corners of the sky, a phenomenon no telescope has yet detected, but one that haunts the edges of cosmology's imagination. Then there's the eerie cosmic shadow hypothesis. Some theorists suggest that if the universe does have an abrupt edge, it might cast a shadow not of darkness but of unexpected cold. Just as a mountain blocks sunlight, leaving a chill in its wake, a cosmic boundary could leave a detectable dip in the temperature of the cosmic microwave background. Astronomers have scoured the data for such anomalies like the infamous cold spot, but so far, nothing definitive has emerged. Critics argue these quirks could just as easily be statistical noise or the remnants of colossal collisions between space-time bubbles in the multiverse. The truth is, we're trapped inside our cosmic horizon like sailors adrift in an ocean, wondering if land lies beyond the curve of the Earth. Even with telescopes powerful enough to glimpse the first stars, we're shackled by the laws of physics. Light from the universe's hypothetical edge hasn't had time to reach us, and if expansion keeps accelerating, it never will. The frontier might always be just out of sight, leaving us to wonder if the cosmos is infinite, finite but unbounded, or something stranger still, a shape beyond our geometry, waiting for a mathematics we haven't yet invented to reveal its edges. Dark energy didn't just show up, it's been here all along, woven into the fabric of space itself. But here's what defies logic. For billions of years, it was a whisper drowned out by the roar of matter's gravity. Only recently, cosmically speaking, has it surged to dominance, twisting the universe's fate toward runaway expansion. This eerie timing is called the coincidence problem, and it's one of the most baffling riddles in modern cosmology. Why now? Why, after nearly 14 billion years, has dark energy's push suddenly eclipsed everything else? Rewind to the universe's early chapters. For the first few billion years, matter, both the ordinary atoms we're made of and the invisible cloak of dark matter, ruled the cosmos. Gravity's pull was king, slowing the expansion inherited from the Big Bang. Galaxies formed, clusters merged, and the cosmic web took shape under matter's firm grip. Dark energy existed, but its repulsive force was negligible, like a gentle breeze against a tidal wave. The math is stark. During this era, matter's density was thousands of times greater than dark energy's. But density changes as space expands. Matter dilutes, its particles spreading thinner as the universe grows. Dark energy, bizarrely, doesn't. Whether it's Einstein's cosmological constant or some more exotic field, its energy per cubic centimeter stays stubbornly the same. Picture a balloon inflating. The number of dots on its surface matter stays constant, so they spread apart. But the air inside dark energy maintains its pressure, growing more dominant as the balloon stretches. Around 5 billion years ago, the scales tipped. The universe had expanded enough that matter's density dwindled to match dark energies, and then catastrophically fall below it. That's when acceleration kicked in, flinging galaxies apart faster and faster. The timing feels unnervingly precise. If dark energy had dominated earlier, galaxies would have been ripped apart before stars could ignite. Later, and gravity might have reversed expansion, collapsing the cosmos into a big crunch. Instead, we exist in a sliver of cosmic history where the transition is just happening, allowing us to witness both eras. Some theorists call this the Goldilocks window, a fleeting phase where the universe is neither too dense nor too empty, but just right for life to ponder its own existence. But is it really a coincidence? One radical answer is the anthropic principle. We observe this timing because it's the only scenario where observers like us could evolve to ask the question. In a multiverse of infinite bubbles with different dark energy strengths, we'd naturally find ourselves in one where the numbers allow galaxies, and thus life, to form. Others propose dynamic dark energy like quintessence, which could have lain dormant until triggered by some cosmic milestone, like the average density of matter hitting a critical threshold. There's even the ghostly idea that dark energy isn't a force at all, but an illusion caused by our three-dimensional perspective of a higher dimensional universe folding in on itself. The truth is, we're trapped in a single data point, one universe, one timeline, with no way to rewind the experiment. Upcoming telescopes like the Nancy Grace Roman Space Telescope will probe dark energy's behavior across 10 billion years of cosmic history, hunting for drifts in its strength. Until then, the coincidence problem lingers, a reminder that the universe's acceleration isn't just a puzzle of physics, it's a mirror, reflecting how little we understand about the stage on which our existence plays out. What if everything we think we know about gravity is wrong? Some scientists are daring to ask that very question, proposing radical alternatives to Einstein's century-old theory of relativity. Take emergent gravity, a concept that turns our understanding of the cosmos on its head. Instead of gravity being a fundamental force, this framework suggests it's an illusion, a side effect of the way information is structured in the universe, like how temperature emerges from the motion of atoms. The brainchild of physicist Eric Verland, emergent gravity, argues that what we perceive as gravity is actually the entropy-driven response of microscopic quantum bits embedded in space-time. It's a dazzling idea, one that could, in theory, explain the rotation of galaxies without invoking dark matter. But here's the catch: when put to the test, emergent gravity struggles to match the precise gravitational lensing patterns we observe around galaxy clusters. It's like having a key that fits part of the lock but jams halfway through. Then there's the holographic principle, a notion so audacious it sounds like it's ripped from a sci-fi epic. This theory posits that our three-dimensional universe might be a projection of information stored on a two-dimensional boundary, like a cosmic version of a movie screen encoding every detail of the film playing before it. The math is elegant, suggesting that black holes, quantum mechanics, and even gravity itself could be holographic illusions, but does it hold up to reality? When applied to cosmic expansion, holographic models often clash with the universe's observed flatness or fail to reproduce the exact clustering of galaxies. It's as if the theory paints a breathtaking mural, only for astronomers to point out entire sections where the colors bleed outside the lines. These radical ideas aren't alone. There's also conformal cyclic cosmology, championed by Nobel laureate Roger Penrose, which imagines an endless cycle of universes where the distant future of one becomes the Big Bang of the next. Or fractal cosmology, where the distribution of matter repeats at vastly different scales, from galaxies to galaxy clusters. Each of these models offers a tantalizing escape from the conundrums of dark energy and inflation, yet none have yet produced the smoking gun predictions that would dethrone the standard model. The problem isn't a lack of creativity, it's data. Modern telescopes like Planck and JWST deliver exquisitely precise measurements of the cosmic microwave background, galaxy distributions, and supernova distances, a flood of evidence that any viable cosmology must explain. So far, the standard model, with its dark matter and dark energy, remains the best fit, however unsatisfying those mysteries may be. That doesn't mean alternative cosmologies are dead ends. Every revolutionary theory starts as a fringe idea. Einstein's relativity upended Newton's clockwork universe after all. The difference: relativity made testable predictions, like starlight bending around the sun, that were later confirmed. Until emergent gravity or holographic cosmology can do the same, they'll remain fascinating thought experiments, glittering in the dark like distant stars we can't quite reach. What makes this pursuit so vital isn't just the chance to rewrite textbooks. It's the reminder that science thrives on dissent, on the heretics who dare to ask, what if we've been looking at it all wrong? Even failed alternatives sharpen our understanding, forcing us to question assumptions and refine our models. So while these ideas may not yet match the universe we observe, they keep the doors of discovery wide open because the next great revelation might be hiding in the equations we haven't dared to write. We've mapped billions of galaxies, traced the echoes of the Big Bang, and yet everything we've ever observed is just a speck in what might be an unfathomably larger reality. The observable universe stretches 93 billion light-years across, but that's not the edge of existence. It's merely the horizon of our vision, the limit of how far light has traveled since the cosmos began. So what lies beyond? The answer isn't just unknowable, it's potentially stranger than fiction. One possibility is that the unseeable universe looks remarkably similar to ours, an endless repetition of galaxy clusters and cosmic voids stretching into infinity. But there's no rule saying it has to. Inflation theory suggests that distant regions could have experienced wildly different expansion rates, creating pockets of space where physics itself operates under alien rules. Imagine bubbles in a boiling pot, each with its own distinct properties. Some might harbor stronger dark energy, causing space to rip apart at breakneck speed, while others could have collapsed back into singularities long ago. We'll never see these regions. They're receding faster than light can bridge the gap, leaving us forever isolated in our own cosmic neighborhood. Then there's the Hubble bubble hypothesis, a controversial idea that our local patch of the universe might not be representative at all. What if dark energy's strength varies across space, and we just happen to reside in a quieter zone where expansion is unusually slow? This could explain why some measurements of the Hubble constant disagree. We might be like sailors mistaking a calm bay for the entire ocean. Critics argue there's no evidence for such a bubble, but if true, it would mean our cosmic yardsticks are flawed, calibrated to a region that's the exception rather than the rule. But the real mind-bender is this. If other regions exist with different expansion rates, could entire civilizations rise and fall in universes where time flows at altered speeds? In a pocket where dark energy is weaker, gravity might have pulled matter into galaxies far sooner, birthing stars and planets billions of years before our sun even ignited. Or in hyper-expanding zones, space might stretch so fast that complexity never gets a chance to form, leaving behind a barren, eternal void. The cosmos beyond our view could be a mosaic of realities, each obeying its own rhythm, its own fate, forever separated by distances not just of space but of fundamental physics. The cruel irony is that we're trapped behind a veil we can't pierce. No telescope, no matter how advanced, will ever catch a glimpse of these realms. The light from them will never reach us. The space between us grows too fast, too relentlessly, and so we're left to wonder, to theorize, to stitch together clues from the sliver of reality we can observe. Perhaps the greatest lesson isn't just about what lies beyond, but how much humility it takes to stare into the dark and admit, with equal parts awe and frustration, that some mysteries might remain forever out of reach. The James Webb Space Telescope is already rewriting cosmic history, but it's just the beginning, with its infrared eyes peering deeper into space and further back in time than ever before. JWST has spotted galaxies so ancient they shouldn't exist, black holes too massive for their eras, and chemical signatures that challenge our timeline of cosmic dawn. Yet this technological marvel is merely the vanguard of a revolution in cosmic exploration. The Vera Rubin Observatory, now coming online in Chile, will scan the entire southern sky every few nights with its 3.2 gigapixel camera, creating a decade-long movie of the cosmos that could reveal subtle changes in dark energy's push or catch the flicker of primordial black holes drifting through our galaxy. Meanwhile, the European Space Agency's Euclid spacecraft is mapping the distribution of galaxies across 10 billion light-years with unprecedented precision. hunting for distortions caused by dark matter's gravity and measuring how cosmic voids grow over eons. Its findings could settle whether dark energy is truly constant or evolving, a question that determines whether the universe faces a slow freeze or a violent rip. On the horizon loom even more ambitious projects. The Square Kilometre Array radio telescope will detect hydrogen from the universe's first billion years, tracing how the cosmic web took shape, while NASA and Nancy Grace Roman Space Telescope will study supernova so distant their light reveals expansion rates from when dark energy first gained dominance. These aren't just tools, they're time machines, letting us test theories against the universe's own archive. When astronomers compare JWST snapshots of early galaxies with Euclid's dark matter maps and Roman's supernova catalogue, they're assembling a multidimensional puzzle spanning the cosmos' entire lifetime. Discrepancies between these datasets could reveal flaws in our standard model as profound as when quantum mechanics shattered Newtonian physics. Already, anomalies like the Hubble tension and unexpected early galaxies suggest we're on the verge of a paradigm shift, one where dark energy might interact with dark matter, where gravity's rules change across cosmic epochs, or where entirely new physics governs the universe's fate. The most exciting possibility that the answers won't come from where we're looking. Just as dark matter was discovered through the stubborn refusal of galaxies to obey gravity's known laws, the next breakthrough might emerge from an observation so baffling it forces us to rethink reality's foundations. Perhaps we'll find evidence of higher dimensions in gravitational wave patterns, or spot quantum imprints in the cosmic microwave background that point to a cyclic universe. Every unsolved question is a doorway, and with these new instruments, we're not just knocking, we're kicking them open. Science thrives on the edge of the unknown. For every mystery solved, new ones emerge, each more profound than the last. That's the beauty of cosmic exploration. The universe will always have secrets, but with each generation of telescopes, we get closer to understanding our place in the grand tapestry of space and time. The questions may be ancient, but the answers, those belong to the future. These 25 unsolved mysteries aren't just gaps in our knowledge, they're chasms tearing open the fabric of our understanding and forcing us to question everything we thought we knew about the cosmos. From the deceptive simplicity of dark energy to the ghostly influence of extra dimensions, each unanswered question is a thread in a grand tapestry, woven with equal parts wonder and frustration. The Hubble tension, the cosmic coincidence problem, the eerie uniformity of the CMB, these aren't academic footnotes. They're glaring signs that our current models are incomplete, whispering of physics beyond Einstein, beyond quantum mechanics, beyond anything we've dared to imagine. And that's exactly what makes this moment so thrilling. Every anomaly is an invitation, a chance to rewrite the rules, to peel back another layer of reality and glimpse the universe's hidden blueprint. Forget what you've heard about settled science. Cosmology is a frontier, wild and uncharted, where today's heresy could be tomorrow's textbook truth. The greatest discoveries often begin with someone staring at a discrepancy and daring to ask, what if we've been wrong all along? That's how dark energy was found. That's how inflation theory was born, and that's how the next revolution will start, not with a bang, but with a persistent, nagging inconsistency that refuses to fade. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That's the heartbeat of cosmology. It's not just about mapping galaxies or measuring redshifts. It's about confronting the vast unknown with equal parts humility and audacity. So here's my challenge to you. Pick one of these 25 mysteries, the one that keeps you awake at night, and dive deeper. Maybe it's the phantom pull of dark matter or the universe's unsettlingly perfect flatness. Maybe it's the chilling possibility of a big rip tearing apart atoms in the final seconds of time. Whatever it is, let it ignite your curiosity. Because the universe isn't just expanding, it's revealing itself one paradox at a time. And who knows, the next great insight might not come from a telescope or a supercomputer, but from someone watching a video like this, staring at the stars and asking the right question. So tell me in the comments which of these cosmic riddles haunts your imagination. The conversation doesn't end here, it's just beginning.